In this video, I'd like to talk about the Z transform, which is used very commonly in digital signal processing applications. It's often taught in university very theoretically, and today I'd like to go through the very practical application of the Z transform. I use it myself nearly every day or every time I have to design a filter or analyze a discrete time system, and I'd like to show you how to do that, and then also implement that on an embedded system, for example using an STM32 microcontroller. So let's get started. As is usual for my DSP videos, I'll be using this LittleBrain board that I designed myself with an STM32F4 microcontroller and various sensors. And this board was actually made by JLCPCB in China and actually manufactured by them as well. Thanks also again to JLCPCB for sponsoring this video. And what you see with the LittleBrain board has actually been assembled and manufactured by JLCPCB in China. Now you can find all the design files and all the firmware in my GitHub repository if you look for the LittleBrain STM32F4 sensor board. And there we have the assembly, Gerber, and firmware folders for you to check out, and also, of course, all the KiCad design files. I'm very pleased to announce that this channel is now sponsored by Altium Designer as well, so thank you very much to them. Altium Designer is actually what I use in my day-to-day work when I design things, for example, like this ESC over here, so pretty high-power designs, and things like high-speed digital boards, which have HDMI, USB 3, and so on. And of course, there'll be still KiCad videos to come, but I will also be focusing a bit more on Altium Designer and why, for me, I prefer that over KiCad, especially when it comes to high-speed designs or things that are just a bit more complicated. In the meantime, there's also a link in the description where Altium is actually offering a free trial of their Altium Designer software for you to use. We'll look at the Z transform overall, at a bit of the theory, but not in depth, and I will link in the description a few videos and articles that'll help you get started if you haven't heard of the Z transform before. I'm assuming some basic knowledge about it and of course some maths knowledge as well. Then we'll look at how we can actually analyze stability properties of discrete time systems or filters, and we'll also look at how to analyze the frequency response. In between, of course, we'll look at actual implementations and tests to verify that the theory we are looking at is actually correct in the real world as well. As I said before, we will not cover much Z transform theory or any derivations. In essence, the Z transform is the discrete time equivalent of the Laplace transform, which we use to analyze continuous time systems. Now, comparing the Z transform to the Fourier transform, we can actually use the Z transform to analyze the frequency response, but also the stability of the system. The Fourier transform usually only gives us a frequency response of the system or frequency analysis. But the Z transform is really helpful in determining if a system will be stable, if a filter will be stable, and so on. So for example, we can analyze discrete dynamic systems. So if we have a discrete model of an aircraft, for example, we can see how the stability changes if we change, for example, the wing shape. Or we can look at digital filters. So very commonly, IIR filters will have some stability issues if you go into higher orders. And the Z transform actually allows us to analyze that. In general, if we have a linear, time-invariant difference equation, the Z transform is the tool to use to analyze the frequency response and stability properties. As I said before, we won't be looking at much theory, but I'd like to tell you how to actually take a Z transform. Even if you haven't heard of the Z transform before, it's actually really simple to apply. Again, we require a linear time-invariant difference equation. For example, this one here. We have an output, which is y, and an input that is x. This could be, for example, a really simple block diagram of the system. We have an input x, this goes into the system, it does something with it, and it produces an output. Now, in discrete time, we don't have differential equations, we have difference equations. So something like this. It is simply summing, subtracting, and multiplying with constants. That's why it's linear. So the output is some constant times the input, plus another constant times a previous input, this is the sample at n-1, and then some constant times an output which is delayed by 3 samples. And this is actually really simple to understand. The question is then, of course, how we look at the stability and frequency response. But before that, we need to know how to take the Z transform. So here are the two main rules, so to speak. When we start in discrete time, so in the time domain, we typically denote our variables with a lowercase letter, and then square brackets indicate the sample number. So for example, y square brackets n would indicate that it's, for example, the output y at sample n. Now when we take the Z transform, we simply replace that little y by a big Y. And that indicates that it is now the transformed variable. Alternatively, sometimes we just put a bar across the variable, and that indicates it's been transformed. Now, the second rule is that if we have a shifted sample, for example, y at shifted n minus k, and k might be 1, 2, 3, and so on, we typically take the Z transform, so we transform it to the big or uppercase letter, and then multiply by z to the minus k, and k being the shift amount. So if this is y of n minus 1, it would be capital Y times z to the minus 1. And that's pretty much all we have to know to apply these rules and take the Z transform. And this might sound a bit confusing at first, but let's go through an example. So here we are again with a pretty much randomly chosen discrete time difference equation. We have the output y and an input x. Now remember our two rules of taking the Z transform, so this lowercase y in discrete time goes into an uppercase y indicating it's transformed. Now it's no longer a function of a sample number, it is the function of z, which is our transform variable. We do that with y of n, x of n, but then we have these shifted samples of xn minus 1 and yn minus 3. And as before, we take the simple transform, so x goes to x of z, capital X of z, but then we have to multiply by z to the minus 1 because we've shifted by one sample here, and here we have to multiply by z to the minus 3 because we've shifted by 3 samples. In essence, the z operator is a time delay or time advance operator. So time delay if it's z to the minus something, and time advance if it's z to the plus something. We can, after we've taken this z transform, that was pretty much it, we would like to just rearrange and combine the terms, and that's what I've done at the bottom here. So I've put everything to do with y on one side, and everything to do with x on another side. A very important concept is that of the transfer function, and that is essentially just an input-output relationship of a certain system. We can express the input-output relationship in terms of the discrete time domain using just, for example, samples y of n is x of n plus something else. But we can also do that in the z domain as well. And that is simply a ratio of the output transformed over the input transformed. And we call this typically g of z, and that is the transfer function. And in our case, that actually rearranges for our example discrete time difference equation to alpha plus beta times z to the minus 1 divided by 1 minus gamma times z to the minus 3. And this is what we call our transfer function. And again, this is an input-output relationship over the system. A very important concept, not only for the Z transform, is that of poles and zeros. And just briefly explained, and not in much detail, the zeros are the roots of the numerator polynomial of our transfer function, and the poles are the roots of the denominator polynomial of g of z, or our transfer function. And here again is our example transfer function. So if we solve the top equals 0, we get the zeros, and if we solve the bottom, this denominator equals 0, we get the poles. And again, we show an example, and for example, if you want to find the 0 of g of z, our example transfer function, remember the numerator was alpha plus beta times z to the minus 1 equals 0. Now rearranging that for z, we get that the 0 is at minus beta over alpha. And we can use the same method for the denominator to find the poles. Typically, we also say the number of poles is actually the order of the system. So if the system has 2 poles, it's a second order system. Now that we know how to quickly take the Z transform and actually seeing that it isn't that hard, let's move on to what we can actually do with the Z transform. And one of the main things is actually to do a stability analysis. So, for example, if we supply an input to a system, a discrete time system, what will happen to the output? Will the output tend to infinity or minus infinity, or will it settle at some value, for example, 0? And that, in essence, is what stability is all about. So a system is said to be bibostable if bounded inputs produce bounded outputs. And you can see that in these pictures here. Again, we have an input x of n going through our discrete time linear time invariant system and producing an output y of n. And for example, if our input is something like this, we have discrete samples and we pass this an input and it goes to 0. If the system is stable, we expect that our output also settles at some value, for example, 0. And this means we have a stable system, and the question is how to analyze that. Now, in the other case, if our system is unstable, we might supply the same input or a certain input which is bounded, it doesn't go to infinity, but the output, very quickly or very slowly, doesn't really matter, but if it's unstable, it'll tend to infinity or minus infinity. And that's typically not a good thing. So in essence, we can determine if a discrete time system is stable or not using the Z transform, and quite quickly. The method we're going to use is we start with a difference equation, for example, one of a filter or a discrete time system. We take the Z transform, we then make our transfer function, which gives us our input-output relationship, and then we find the poles. Now, without proof, I'm going to tell you that if all poles are within the unit circle, that's a fancy way of saying that the magnitude of all poles individually is less than 1, the system is stable for bounded inputs. And we'll go through an example just to re-emphasize what this actually means. So typically you will see something like a pole 0 plot like this. So for example, if we have a stable system, it might look something like this. This is the unit circle I talked about. This is an Argand diagram with the imaginary axis here and the real axis here. Now our poles are indicated typically by little x's, and the zeros are indicated by zeros or noughts. If all the poles lie within this circle of magnitude 1, then we're fine. Now, even if a 0, for example, lies outside, that is absolutely fine. The only thing that matters for stability are the poles. Now, if only one of these poles is outside of the unit circle, for example, this one here, the whole system is unstable. Even if we have 1,000,000 poles inside the unit circle and just one is outside, the system is unstable. And again, the 0 doesn't matter for stability. Now let's actually use this to analyze the stability of an IIR filter. And I'll talk about IIR filters in a future video, but let's look at a first order filter for this case. So effectively an IIR filter is some sort of digital filter that uses feedback. And typically we'll have a first order filter where the output is some constant times the input, and we take away some fraction of the previous output. So it's using feedback. Now, this is all well and good, but say we can change the parameters, for example, alpha and beta here. We would really like to know quite elegantly, how can we change alpha and beta and still make this filter stable? We don't want any input to produce, for example, an infinite or saturated output. We want this filter to be stable. So our method is, of course, as follows. We start with the difference equation of our IIR filter, then we take the Z transform, remember lowercase goes to uppercase, and instead of being a function of the sample number, it is now a function of Z. When we have a time shift, either forward or backward, for example here, n-1, we multiply, in this case, by Z to the -1. And that's it. That's all there is to taking the Z transform. Then we rearrange, taking the ratio of y of z over x of z to give our transfer function, which we'll call g of z. Now you can see here we have alpha times z over z plus beta. And it's really quite simple to see that we have 1, 0, and that's when z equals 0, and we have one pole. So remember, that's when the denominator equals 0, and that happens when z equals minus beta. Now we remember that the filter is stable, or any system, discrete time system is stable, if the magnitude of all poles is less than 1. Therefore, because our pole was as minus beta, the stability of this particular filter is actually not dependent on alpha. Alpha simply changes a certain gain, but has nothing to do with stability. But we require that the magnitude of beta, which is essentially the magnitude of the one pole we have, is less than 1. And this means that beta has to lie somewhere between -1 and 1. Now, if beta equals 1, or exactly -1 or exactly 1, then we call this system to be marginally stable, but it's effectively still unstable. It'll oscillate. So we need beta to be less than 1, but also greater than -1. Now let's look at this implemented on a real-world system. I would just like to show you the STM32 setup I have for this LittleBrain board, and it's a very simplified firmware I'll be using to demonstrate the Z transform properties. I have my STM32F405 in Cube IDE. I've enabled the crystal oscillator, and there's a 16 MHz crystal oscillator. In the clock configuration, I'm running it at 168 MHz, which is the maximum I can for this chip. I've just enabled one red LED on this pin over here, serial wire debug, and USB. That's pretty much all we'll need. We'll do some processing on the chip, and then send our resulting data over via USB, and then flash an LED just to indicate that we're running and active. Then in our main code, I'll start from top to bottom. I've defined some sample times, for example, for the filter in milliseconds, in 100 Hz, so every 10 milliseconds the filter will run and update and get a new output, and also for the LED, which is on board this board, every half a second that'll turn on and off. So for our filter, the ones we looked at in the examples, we have an alpha value and a beta value, and I've just had these as defines up here. So if I quickly want to play around with these values, I can just change them in these defines. Then we have 3 parts of this filter. First of all is just a struct. I'm programming this in C, so I'm using struct, and that stores essentially the alpha value, the beta value of that filter, and then also the filter's output. So for our first order filter with just one previous output, we can get away with just using one output variable. Now I've done this because maybe I want to play around with multiple different filters, and they each can store their own parameters. Then we have an initialization function where I pass the filter, the alpha and beta, and that then stores it and sets the output of the filter initially to 0. And then we have the main function, which actually then implements our IIR filter, and that returns as a float the filter output. It takes the filter struct and the input to the filter also as a float. Now all I'm doing is implementing this difference equation we looked at before, and that is y of n is alpha times x of n, which is the input, minus beta times y of n minus 1. So in other words, in C, the filter output is the constant, which is the alpha value, times the input, which is the current input, minus beta, which is another constant, times the filter's previous output. And we store all of that in the filter's current output and then return it. And that's all there is. I initialize the filter, And then I essentially have my infinite while loop, and one of those if conditions is when a certain amount of time has passed, those 10 milliseconds in this case, I will trigger this in this if statement, update the filter, and send the filter input data and the filter output data via USB as a virtual COM port, and that's about it. The other if statement just toggles the LED. So really, really simple. So to check stability, I'm going to play around with the alpha and beta values, or rather just the beta values. And to show you that this filter is indeed stable with beta having a magnitude less than 1, I will set it to 0.1. As an input to the filter, I'm just going to pass a simple sinusoid with a frequency of 0.05 Hz. And I'm actually toning down the sample rate quite a lot so we can actually see what's going on. Then I'll be using this serial oscilloscope, which captures the data coming from the USB via the STM32 and plots it on a grid, and I'll show you that in just a second. So yeah, that's pretty much what we're doing. We're setting beta to 0.1, alpha to 1, and feeding in a very slow sinusoid and seeing how the output behaves. And just briefly, the way I'm actually generating these sinusoid samples is right here. It's very crude and not very elegant, but I'm setting the filter input to be a certain amplitude, so 10 in this case, and I'm using the standard C math functions for floats. This is essentially just 2 pi times the frequency times the current runtime. And that's about it. So pretty crude, not very elegant, but it works. So I've uploaded the code via the ST-Link to the LittleBrain board. As you can see, the code is running, the LED is flashing, and here I have my serial oscilloscope plotting the input-output data. As you can see, of course, the sample rate is quite low just to make sure we can see what is going on. But as you can see, for the input, which is just a simple sinusoid, the filter is essentially doing its job, and not being unstable, which is what we predicted for those alpha and beta values. Now for the unstable filter, I'm going to change beta to be just 1.05. So this means the pole is just outside the unit circle and giving an unstable filter. And we'll see that in just a second when we run this as the code. Again, I'm passing in a same sinusoid as an input with the same frequency as before at 0.05 Hz. And we're expecting this filter to now be unstable. So let's check that out. So here we now have the unstable IR filter running. And going back to the serial oscilloscope, we can see the input-output behavior. So as you can already see, the red curve is actually the input, and now the green curve is the output, and that's already oscillating, and as you can see, now it's actually growing. This is because the magnitude of beta, as we calculated, is actually puts the pole outside the unit circle and makes this IR filter unstable. As you can see, because I've slowed it down so much, we can actually really see how nicely exponentially this is growing and becoming unbounded. As you can see, the filter input is still bounded. It's just a simple sinusoid with a fixed magnitude, but the output is growing until the floating point variable is saturated. And this really nicely confirms our Z transform theory that we can see when filters become unstable and when they are stable themselves. So this is pretty cool to see. Now that we've covered stability and how we can analyze that with the Z transform, the second main idea of the Z transform, or what it's useful for, is actually frequency response analysis. Now, if you haven't heard of that before, this is one of the most useful things you can do with the Z transform, or generally in engineering. So for example, for a linear time-invariant discrete time system, we can pass a sinusoidal signal of magnitude A and frequency f into the input of our discrete linear time-invariant system, and it turns out the output of the system is then also a sinusoidal signal of the same frequency. What changes is actually that the magnitude changes, either stays the same, is smaller or larger, and we might introduce some sort of phase shift. But the frequency is the same. Now the Z transform lets us characterize the entire input-output behavior of the system in terms of frequencies for all relevant frequencies, and that's what we call the frequency response. And here's that just drawn up really simply. So let's say we have some sort of sinusoidal signal at the input with magnitude A, we pass that into our linear time-invariant discrete time system, and we look at the output. Now the output, for example, just in a random case, the output might be scaled, so it could be larger, and we call this output magnitude B, but we might also introduce some sort of phase shift, so there might be a little delay between the output and the input, so it could be positive or negative. And that's what we call phase shift, or phi. Then we can determine some things called the gain, and that's typically the magnitude as a function of frequency, and that's the ratio of the output magnitude over the input magnitude versus frequency. And then we of course have the phase shift, and we typically know that by phi, and that's also a function of frequency. Again, we'd like to know how we can actually get the frequency response starting from a difference equation. For example, that could be from a filter or some sort of discrete time system. As usual, we take the Z transform to get the transfer function, which we'll call g of z. Now, anytime we see z, or z to the -1, or z to the +1, and z to the whatever, we will substitute in place of z, e to the minus jk theta. and k, of course, depends on if it's minus or plus and so on. We can actually use Euler's identity. E to the minus jk theta is actually equal to cosine of k theta minus j sine k theta. And that becomes useful later when we actually have to determine magnitude and phase responses. But before that, theta actually is equal to 2 pi times f, so the frequency of interest, divided by the sampling frequency of the system. Now remember, we are in discrete time, which means we have to sample. So for example, we have an ADC, we'll sample at a fixed sampling rate. That could be, I don't know, a kilohertz, 10 kilohertz, and so on. And that plays a role when we actually do the Z transform. Now, because we are sampling at fs, due to the Nyquist limit, which is fs over 2, now at the maximum value theta can take is when f is fs over 2, which means that theta is actually bounded between 0 and pi. And that is due to the Nyquist limit. Once we've substituted and found g in terms of theta, we can find the magnitude and the phase response by remembering complex number theory. So we take the magnitude and then we find the phase. And of course, we can use Matlab or Octave to do that for us. And I'll show you how to do that in just a second. So again, just an example to reinforce things. We start off again with our first order IIR filter. We take the Z transform and rearrange to find our transfer function. Again, it's alpha times Z divided by Z plus beta. What I typically like to do is actually write the transfer function in terms of Z to the minus 1, or rather in this case, because it eliminates one of the Z's, so we do have alpha over 1 plus beta times Z to the minus 1. And when we substitute in e to the j theta into Z, it makes it a bit easier. Let's start with this. We have our transfer function in terms of Z to the minus 1. We substitute e to the minus j theta into Z, and it turns into this. So we have alpha over 1 plus beta times e to the minus j theta, and that's because of this minus 1. Then remembering Euler's identity, so e to the j theta is actually cos theta plus j sine theta, we arrive at this expression over here. Then we can use basic complex number theory, and then reduce that and to find the magnitude, g of theta, and the phase of g theta, and plot that versus theta. And let's use Matlab or Octave to do that. And I've actually done that before, but I'll show you in just a second how to do that. Octave is the free Matlab equivalent, so to speak, and I've plotted this IIR filter for values of alpha equals 1 and beta equals 0.1. And you can actually see the magnitude response here. So we have some sort of, looks like a high pass filter in a way. And then we also have the phase response here. And notice the units, this is in decibels, and the phase is in degrees, and the frequency is plotted in radians per second. So let's go over to Octave, and there's actually an online version, and I'll show you how to plot this. So here we are on an online version of GNU Octave, and you can go to octave-online.net, and let's just plot some Z transformed transfer functions. The first thing we have to do is define our sample time, and let's say that's 0.01 seconds, which gives a sampling frequency of 100 Hertz. We have to make our Z transform variable, then we have to define our alpha and beta variables. For example, alpha is 1 and beta is 0.1. Then we can actually write our transfer function for our, for example, first order IR filter, and that's alpha times Z divided by Z plus beta. And now simply to plot the frequency response, so that is the magnitude and phase response, we type in Bode of G. And then it takes a bit of time. And here we can see this is our frequency response, so magnitude versus frequency and phase angle versus frequency. And it's as simple as that. Now there are some tips to quickly analyze the frequency response of a Z transformed transfer function. So the DC gain is when theta equals 0, and that means if you remember Z equals e to the j theta, that means when theta equals 0, Z equals 1. So if we just plug in Z equals 1 into our transfer function, we get the DC gain, and the high frequency gain is when theta equals pi, Z equals e to the j theta, so Z is equal to minus 1. So if we plug in Z equals minus 1 into the transfer function, we get our high frequency gain. Now again, let's see this theory in action on an embedded system and see how our IIR filter actually performs with a frequency response on an STM32 microcontroller. So to check for the frequency response, we're just going to look at one single frequency and see if that matches up with our theoretical Bode plot. So I'm increasing the filter sample rate, or rather decreasing the filter sample time back to 10 milliseconds. That gives a 100 Hertz sampling rate, just so we can quickly see what's going on. And again, I'm making the filter stable. So alpha is 1, and I'm choosing beta to be 0.9 in this case. And this makes the poles be inside the unit circle, and therefore the filter should be stable, or rather is stable. And I'm passing in a sinusoid as the input to the filter of 1.59 Hertz. And let me show you why I'm doing that. So I've again used GNU Online, and I've made it show me the Bode plot for this filter with alpha is 1, and beta is 0.9. And you can see that here. And this is the magnitude diagram. And the frequency here is in radians per second. And as you can see up here, 10 rads per second, to get that into hertz, is you divide by 2 pi, and that gives me 1.59 Hertz. And that's why I'm using that in my C code here, just to check at this certain point what is the amplitude, or what should that be. And according to the Bode plot, again, the magnitude is in decibels. It's about, I don't know, just about less than -5. Let's say it's -6 decibels. From decibels to linear, -6 dBs is about half. So, for example, an amplitude of 1 at the input, we should get an amplitude of 0.5 at the output. And this is what our Z transform and our Bode plot is actually telling us. So let's see if that's true by running it in the C code and seeing what the filter actually outputs. Again, here's LittleBrain board running this stable IIR filter, and at a frequency of about 1.6 Hertz, we can see that here the green trace is the output, the red trace is the input. The green trace looks like it's about half of the amplitude of the red trace, and that's about -6 dB. And that's what we got from our Z transform Bode plot, which we can see over here. So we can see at the lowest frequency here, about 10 rads per second, which is about 1.6 Hertz, we get -6 dB. So that looks pretty good.